Good morning, everyone. Thank you all for coming. First of all, I would like to thank the organizers for the great opportunity of presenting our work here. I have to put my hands forward and say that this is very preliminary, so it's really changing on a daily basis, but still we are excited where we started from and where we are going with it. I hope you will share the same views. So as I said we. Say it again? Yes. And but as I was telling before, we know that we're going to converge, we do not know how fast. So in any case, as I said, it's we. So this is a joint research project with Fabio Maccheroni, Massimo Marinacci, and Pierpaolo Battigalli. So in a nutshell, with this research project, we are exploring learning, asymptotic learning, but when two ingredients are present, when information is endogenously generated and there is no ambiguity neutrality. So in particular, we will focus to the case when ambiguity aversion is present. Part of the motivation behind this research project is connected to one of our recent papers, same set of co-authors, and this paper tries to join two ideas. One is the self-confirming equilibrium idea, and the other one is ambiguity aversion, so an idea from decision theory. So self-confirming equilibrium, the static notion, is basically a notion of equilibrium where agents best respond to beliefs. Beliefs are nothing else than they are nothing else over on the set of pure strategy of the opponents, and the key thing is that these beliefs might not be correct, as in Nash equilibrium, they just must be confirmed. So basically, given the profile of strategies in equilibrium, the beliefs that the decision maker uses to best respond must be consistent with the observation that the distributions in equilibrium generate. So for example, the observations over outcomes or utility profiles. In such a notion of self-confirming equilibrium, in such a notion of equilibrium, automatically ambiguity or model uncertainty is generated, because in equilibrium there might be several beliefs that are consistent with the distributions that are defined, describing the equilibrium. So automatically there are several beliefs that the decision maker can have and that can justify that particular equilibrium. So there is room to introduce ambiguity aversion. And ambiguity aversion, in such a setting, what it generates is a status quo effect, in the sense that the decision makers in equilibrium, if he's ambiguity averse, tends to prefer strategies that generate unambiguous utility profiles. So he best responds, the action is still optimal, but the action that turns out to be optimal for each player is basically an action that has the feature of being unambiguous with respect to all the possible probability models describing the opponent's strategy distributions. So the interpretation that we give to such a notion of equilibrium, self-confirming with model uncertainty, is an interpretation of steady state. That is, we think of these static games as basically population games. So an agent from each player is seen as a population. So an agent from a population is drawn, is matched with an agent from another population. They play and they are split, and then again they are matched with somebody else from the other population, and this goes on and on. So basically the notion of equilibrium, self-confirming equilibrium with model uncertainty, this notion we interpret it as the steady state of that particular system. So the decision makers, after playing the agents in populations, after playing for many times, they converge, they have that particular distributions that describes how they choose pure lotteries. And basically, the fact that the optimal actions are unambiguous with respect to all the possible confirmed beliefs is the fact that they learn the probability with which consequences realize. Okay, so we interpret it also as a rest point where the learning path stopped. So in this paper, we are looking at one decision maker, and we are trying to provide a foundation for this learning procedure. Okay. So I will just, after this long introduction, I will just describe briefly the related literature, where I'm highlighting with bold characters the differences. So I mentioned that our paper is actually a prequel to our self-confirming equilibrium and model uncertainty paper, and I'm also citing Klibanov, Marinacci, and Mukherjee, since our decision maker, at least for the presentation today, is gonna his preferences are gonna be described by the smooth ambiguity criterion. There are a few papers related, for example, Kalai and Lehr, that study a somewhat similar, they have a similar analysis of learning, and they explore convergence to a dynamic self-confirming equilibrium. The differences are that they they look at the SEO maximizer. So in our case, we want to introduce ambiguity aversion. And in particular, since they're looking at the SEO guide, they don't have this status quo effect that we're going to have. Fudenberg and Levin, the difference is, well, they study a steady-state learning procedure in recurrent population games, and then they study how can this approximate a static self-confirming equilibrium. The differences are, again, on the preferences of the decision makers, if you wish, of the players, and at the same time, the fact that is lacking this status quo bias effect. The other difference is that they look at stationary environment, where we don't necessarily have to look at such environments to achieve our results, to obtain our results. So our problem is going to be a dynamic decision problem, but first I have to describe the stage decision problem. And the setting we decided to use is the standard Marshall-Runner setup with an extra element, ambiguity. So there are 5 elements that describe the stage decision problem. The first, they are all in bold characters. So the first element is a set, capital A, of actions that the decision maker can take at each point in time, okay? So in particularly within a stage decision problem. Then a state realizes little x in x, and a consequence is obtained by the fact that he played an action little a in capital A and a state little x in capital X realized. So the third element is a consequence function that associates to pair of action and state a consequence. The decision maker ranks consequences according to a utility function, a von Neumann-Morgenstern utility function we'll see in a second, that goes from C, the set of consequences, to the real line. If the decision, well, if we compose U with rho, we obtain a payoff function that basically is just transforming into utils, pairs of actions and states. If the decision maker knew the probability ruling the realization in X, we just assume it would be a standard guy. So its reward function would be an expected reward function, okay, according to the probability that is ruling the realization in X. But this is the novelty, or part of the novelty, we are introducing model uncertainty. Model P is unknown. So given a belief, a prior, over the set of possible probability models over X, the actions are ranked according to the Klibanov, Marinacci, and Mukherjee smooth ambiguity criterion. So the decision maker computes the expected reward for the action according to model P. It distorts it through a function phi, which captures the ambiguity attitudes of the decision maker, and then he averages out these evaluations. The assumption we have on phi, which is the 5th and last element characterizing the Marshall-Runner setup for the stage decision problem, are really mild. We are just assuming that it's strictly increasing and continuous. Before moving on with the presentation, I'd just like to make a couple of technical remarks so that we are sure that what we are dealing here is everything is well defined. So we assume that the payoff function R is bounded so that all our integrals are well defined, and as much as we have a sigma algebra on X that allows us to talk about probability, we need a sigma algebra over the set of probability models over X. And the sigma algebra we take is really standard, is the sigma algebra that makes measurable all the possible probability evaluations. So in order to move to the dynamic decision problem, I need to introduce a bit of notation, which is quite standard. So consider a set Z. Let me anticipate that at this stage, Z can be either the set of actions A or a set of states X. we denote by Z0 the set just containing the empty sequence, okay? And by ZT, the set that contains all history up to time t. The set Z infinity then is nothing else than the set of all infinite histories. An M element of Z infinity is denoted either by Z infinity or as a sequence, okay? When Z is finite, in particular, we will assume that X, the set of states, is finite. We endow Z infinity with a very standard sigma algebra, the one that is generated by the elementary cylinders. Okay? Notice that there is a little small abuse of notation in the sense that we denote finite histories with the same symbol with which we denote elementary cylinders. But clearly, being there a one-to-one relation is really a small abuse of notation. We assume also that there is a probability space where all uncertainty is summarized. For the sake of, for today's presentation, you can also assume that omega is X infinity, and sigma omega is nothing else than the sigma algebra generated by the elementary cylinders. We will assume then that there is a state process X that for each omega in omega associates an infinite history of state realizations, okay? If P is the true model ruling the realizations of events of omega, then this blackboard P induces a true probability model over the set of states, infinite state histories, okay? The feedback function. This is the last element, the sixth element that will allow me actually to discuss the dynamic decision problem. So the dynamic decision problem is nothing else than the stage decision problem repeated infinitely many times, okay, for each time t in n. And the feedback function is what is going to be the true dynamic element. Because for each pair of actions as state, it will give a message M. And this message M, we will see in a second, is gonna be used by the decision maker in the subsequent period to inform the choice of his action. So as I mentioned, the recurrent decision problem is described by the same elements of the static decision problem plus the feedback function. We assume that the feedback function relates to the elements of the stage decision problem. The only assumption that relates it is that this condition with rho is satisfied. That is, consequences are observable. Everything, so observing a consequence does not inform the decision maker more on the true state that realized than what already the message is communicated. In receiving the consequence, there is no information that was already embedded into the message the decision maker received ex post, after it chose action A and state X realized. The feedback function, once an action A is chosen, induces an ex post information partition, which is endogenous because, again, it depends on the action A chosen. So the decision maker, by observing, for example, message little m, knows that all the possible states that might have realized are the one that, paired with action little a, deliver the message little m. Okay? We will say that there is on-action independence if the message provided by the feedback function is independent of the action chosen by the decision maker. And an important example of on-action independence is when there is perfect feedback. That is, the decision maker ex post is told which state of the word realized. Yeah?
Suppose I have two Ellsberg arms and I get repeated opportunities. So
yes.
So to lead you. Yeah. So I just understand action independence. So if I were not, say, I naturally think, if I were not to choose the uncertain arm, as it were, I never got to really know what is going on in there. But you were saying.
So you made two important points. The first point that is in your remark is that what I'm gonna learn in terms of states that realize depends on the action that I'm taking. So if I'm always choosing to bet on the known earn, if I had two earns, then I will never learn anything about the unknown, about the earn that contains bold in unknown proportions. And the second thing that you mentioned is exactly on action independence, if I understood correctly, because, or is leading me to discuss on action independence in this context, because when will I have on action independence? For example, with perfect feedback. I will bet on a color, a ball is drawn from the urn, the color is revealed, and I'm told not if I win or lose, like in the example, but what was the color of the ball drawn. Did I answer? Benissimo. So, Ellsberg urn, let me already mention to you that I didn't choose, just to make your life hard, to switch from red to black for the known proportion color. But big R was denoting the expected payoff function, so I had to switch to capital B. So two actions, we just limit ourselves to two actions, betting on black or betting on yellow. And basically, our urn contains either black balls, green balls, or yellow balls. The consequence function is a function that is going to pay $1 if the bet, if the color over which the decision maker chooses to bet is the color of the ball drawn, and it gives, the consequent function gives back $0 if the color of the ball over which the decision maker chose to bet is different from the color of the ball drawn. The utility function, we will consider it normalized, so 1 to $1 and 0 to $0. And here, the message the decision maker will receive will be just if he won or lost. It will not be told what was the color of the ball that was drawn. So mathematically, in this case, the feedback function coincides with the consequence function. Notice that if the decision maker chooses to bet over black, then his exposed information partition will tell him just that either that if he won, that the color of the ball drawn was black, or if he lost, that it was either green or yellow, and vice versa. Notice that information is endogenous in the sense that is influenced by the action chosen. If the decision maker opted to bet on yellow, his exposed information partition will be either yellow was the color of the ball drawn, or it was either black or green. Okay. So an element that is important to introduce is the information states, are information states, because those are exactly capturing the information the decision maker have at time t, and are capturing the information that is going to inform the choice of his action. So at time 1, we are just saying that the decision maker has no data. He has no information, so 1 point. At time t strictly greater than 1, his information will consist of a finite history of actions he took, so we are assuming that he has perfect recall, and a set of, and a finite history of messages, the one that he received by playing actions containing the finite histories at minus 1. A strategy is nothing else than a sequence of functions that, for each information state, give back to the decision maker, prescribe to the decision maker an action to take. So here, our dynamic decision problem is basically describing a myopic agent with perfect recall and a prior mu that chooses at each point in time t an action. We will assume that the choice is optimal, but is optimal according to his belief. And his choice is based on the information he accumulated up to t minus 1. This information, once again, is the finite history of his past actions, he has perfect recall, and the finite history of messages that he received up to t minus 1. Alternatively, one way in which we can look at this dynamic decision problem is, instead of a myopic agent, a sequence of decision makers. For example, you can think of, I think, central bankers or public officer in a regulatory institution that serve for 1 year term. Clearly, to put this situation back there, we need two elements. All the decision makers must share the same common prior, and they must have access to a public history, where the public history is for them, is for the sequence of decision makers. They observe what their predecessor did and what message they received. So, here. So, the state process X, given the dynamic structure I just described, the feedback function, and the strategy as a sequence of functions that map information states to action, delivers a trivariate stochastic process, or just a collection of free stochastic processes. Action process, A alpha T, message process, M alpha T, and information process, S alpha T. Notice that the free, and then I'll describe it more formally, all three processes depend on the strategy the decision maker selects. Because again, information is endogenously generated. It depends on the strategy the decision maker chooses. So I'm going to talk about information channels. They are going to be functions that map finite histories to information states. I'm going to tell you also how they are defined. They are defined recursively, and I will give you the formally. And I will define them formally. But before doing that, let me tell you how this process works. So at time 1, the decision maker has just one information state, S1, no data. So his strategy prescribes him just one deterministic action. A state of the world, a state X realizes. And then, given the feedback function, this delivers the decision maker a message. Okay? The message plus the action, the message plus the state, the message plus the action, is going to determine the exposed information, and therefore the information state that the decision maker has at time t equal to 2. And then the procedure starts again. The information channels, the sequence of information channels, allow us to define these processes in terms of the state process. How are these information channels defined? They are defined recursively. So the first one is our initial condition would be the first channel, Xi alpha 1. So Xi alpha 1 will map from X0, so no history, empty sequence, to S1. Remember, just 1 point, no data. Then Xi alpha 2 will basically associate to each state that realizes in 1, the state that realized, the message that realized, and the action that was taken. Okay? And then, recursively, you can define these information channels that, again, connect states to the information states the decision maker receives. In general, information channels, once more, they depend on the action, the strategy the decision maker adopts, and more precisely, they just depend on the strategy up to time t minus 1. When there is on strategy independence of feedback, the information channel is independent on the strategy. So in that situation, you achieve a separation between the information, inference, and the decision. Okay, a particular case in which you can achieve on strategy independence of feedback is when you have perfect feedback. So you are told the state that realized at time t minus 1. An information state, notice, yields a particular T information set. What it means? If I'm told that ST realized, that is, given my action, I'm the decision maker, and given the message, and I'm told also the messages that I'm received, then I can infer that the histories that are plausible with this particular information state are just the one lying in this set. In particular, if I'm also told that the information state was achieved via the information channel Xi alpha t, then basically I'm looking at the inverse image of the information state via the same information channel. Okay? So this is all to say that information channels in particular induce a state identification correspondence. That is, a map that associates to each finite history a set of all the possible finite histories that are compatible with the finite histories I started from. In particular, the identification correspondence induces a partition over the set of finite histories. This partition is nothing else than splitting finite histories into all the possible finite histories that are compatible with each other. Okay? So this partition induces also a sigma algebra, and this sigma, an algebra because it's finite, and this algebra basically allows the decision maker to understand which states are plausible. For example, in the early example, the algebra at time 2 will contain, for example, products, if black was chosen, of these sets. Either you know that in the first state black realized, if you bet on black and you won, and in state 2, then maybe just green and yellow realized since you didn't win. Okay? We could enrich this setting. We could introduce exogenous information. We could also make preferences time-dependent by making time-dependent ambiguity attitudes and the reward function. We just decided to focus on the time-invariant case, but I confidently can say that it wouldn't change much our result. Given that I specify now, because all I did up to now was really notationally heavy and cumbersome maybe, but all I specified was basically a filtration, yes, thank you, a filtration that is dependent on the strategy chosen by the decision maker. That's all I did. And the decision maker is using that information to inform his actions at time t. So now I have to basically start to do the last part of my sentence, that is to see how this information influences the decision maker when he's choosing. So, given a probability model P, I will denote by P given sigma alpha t the regular conditional probability of P. And since the true probability model P bar is unknown, the decision maker has a subjective prior over the set of probability models. The predictive, well, the predictive is nothing else than the probability induced by the prior over the set over the history of states. It's also called the barycenter of the prior mu. And given a prior, of course, I will talk about the posterior. So given sigma alpha t, I will denote the posterior of mu by mu sigma alpha t. And basically, this slide is saying that the posterior we are considering is nothing else than the standard posterior, okay? Standard notion of posterior. How does the decision maker evaluate an action? Well, at each time t greater or equal than 1, he evaluates it according to the smooth ambiguity criterion. But notice that he's incorporating in that criterion the information he received. Another way in which I could rewrite the same criterion, this is just a conceptual detour, would be by conditioning rather than the sigma algebra sigma alpha t, I could condition over the information equivalently over the information states. Okay, this is all. The only difference is what I'm conditioning with respect to it. So our notion of self-confirming equilibrium. The notion of self-confirming equilibrium we are dealing with as just one fundamental, one key feature that needs an extra piece of notation. It's a notion of weakly confirmed beliefs, and it relies on a notion of local absolute continuity. That is, P is locally absolutely continuous with respect to Q, given alpha, if whenever P gives strict positive probability to an alpha to an element E in sigma alpha t, also Q does the same. So a strategy is a self-confirming equilibrium strategy if there exists a prior such that its posterior is the true model is absolutely continuous with respect to the posterior, locally, given alpha, and the strategy itself is optimal. Okay, so there are the two key features of self-confirming equilibrium: the optimality condition and the weakly confirmed beliefs notion. Here, this notion is just saying that the beliefs of the decision maker are consistent in a weak sense with respect to P bar. That is never going to observe an event, this decision maker, that he gave probability 0 to. Okay? This is an equivalent version in which I can rewrite the same concept. The only difference would be that I'm conditioning with respect to the information state. So an example, consider the earned model I just described. Assume that the support of mu are just IID models. So then I can identify them with their marginals. Okay? Consider also the standard thing. Assume that we are told that black balls are in the proportion of 1/3. So what is unknown is the proportion of green and yellow ball. And assume that the true model is the uniform model. Then the decision maker could entertain two extreme models. That is, the one that gives probability 0 to the fact that there are yellow balls, and the one that gives probability 0 to the fact that there are to the event that there are green balls. And assume that this prior then is uniform over these two extreme models. Notice that the true model is not in the support, but the predictive coincides with the true model. In this situation, betting over black is a self-confirming equilibrium, both for an expected utility guy and for an ambiguity-averse guy. And the reason is that for the ambiguity-averse guy, betting on black is unambiguous, and it gives a utility of 1/3, no matter what. On the other end, betting on green and yellow, given these two models, has an expected utility of 1/3, sorry. But given that there is ambiguity aversion, so phi is concave, the final evaluation is below 1/3. For a SEU guy, instead, given that his predictive coincides with the true model, each strategy that, for example, prescribes to bet on black up to time n and then switching to yellow is also a self-confirming equilibrium strategy. Because if he bets on yellow, for example, at time t equal to n, if he wins, he's going to learn what he thinks is the true model. That is, there are 2/3 the proportion of yellow ball is 2/3, and if he loses instead, he's going to rule out the possibility that yellow balls are there, and he's going to switch back to black, because there is no possibility of betting over green. Yes?
Why does he bet on black first? He doesn't learn anything.
Say it again?
He learns from betting on black?
No, he doesn't learn from betting on black.
He's impatient, right? Why wouldn't he bet on yellow first and learn the proportion? There's options now. There's something I don't understand.
So an ambiguity averse one or an ambiguity? Okay. So if he bets on yellow, so according to one model he receives 2/3. According to the other model he receives 0. These two utility profiles are with probability 1/2 and probability 1/2. Now, since it's ambiguity, so in expectation they are 1/3, right? But since it's ambiguity averse, it dislikes this variability in the model, right? Okay, so that's why from time 1 is not optimal for him, because the gain from experimenting is outweighed, because it's myopic. The gain from experimentation is outweighed by the fact that he has to bet over an ambiguous profile, okay? In the sense that he doesn't consider the fact that he's going to learn the model and eventually.
And why? So why is that? Did you assume that at some point and I just didn't notice, or?
So, you see.
It's hidden in your definition.
Yes. So you see, or maybe here, he chooses the optimal. You see the optimal action that maximizes his utility at time t. So the future streams.
The VT doesn't include anything about the future.
No, you see, it's just the today's reward.
So why do you assume this?
So because we wanted to, that's a good point. So one is an interpretation of a sequence of decision makers. The other one is, the most important instead motivation behind this assumption is the fact that we wanted to study, say in a pure setting, learning when information is endogenously generated. So the possibility that there is a gain from experimenting could also influence this learning in the limit. And so we did want to see if in the first place we could achieve learning and then eventually introducing. But we are working on that, and I have a final slides on that. Okay. So learning. Yes, thank you. So we will denote by P alpha the probabilities restricted to the algebra of alpha observable events. So the events that can be observed by playing strategy alpha. We will say that two models are alpha orthogonal if they are eventually distinguishable. So basically they are orthogonal when restricted to sigma alpha, when we just look at the restriction to sigma alpha. And I denote, given the true model P bar, the set of alpha orthogonal model by orthogonal alpha P bar. On the other hand, the models that are observationally equivalent, that is, that they coincide with the true model over sigma alpha, are denoted by sigma alpha P bar. Our first result is that learning can happen. That is, the decision maker will give probability 1 in the limit to all the models that are observationally equivalent, given strategy alpha, to the true model P bar. This happens only if two conditions are satisfied. Let me discuss them in English. The first one is that at least one model, deemed possible by mu, that is, that lies in the support of mu, is observationally equivalent to the true model P bar. That is, you don't need the true model P bar to be in the support of mu. You just need a model that is observationally equivalent to P bar. And then models are partitioned into two sets. The one that are in the support, the one that are observationally equivalent, and the one that are alpha distinguishable from P bar. The idea is then the decision maker at limit gives probability 1 to the alpha observational equivalent model, the one that are observationally equivalent to the true model, and then is learning the true probability over the alpha observable events. And this is what the corollary is saying, because the predictive of the posterior is converging to the, just 1 minute, to the probability, to the updated probability of the true model. The other results that I will just discuss in English, basically without discussing this notation, is that the value of a strategy converges to its expected value at the limit. Okay, so this is nothing else than the certainty equivalent of the smooth ambiguity criterion. So in the limit, the learning results I discussed before implies that even under ambiguity, the strategy that is played over and over again by the decision maker becomes unambiguous because its value converges to the expected utility evaluation of that strategy. So basically, it's providing a learning foundation to the results I was describing before in our other results, that in the equilibrium, the strategies that are equilibrium strategies are unambiguous. They deliver the same expected utility. We have also some comparative statics result, but I'm out of time, so I should stop here.